Professor Koubaa is the director of the Research and Initiative Center and the leader of the Robotics and IoT Lab at Sultan University. His work specially focuses on data science, unmanned system, deep learning, robotics, and IoT. Today's presentation is about leveraging AI for unmanned aerial systems deployment strategies. Professor Koubaa, the floor is yours.
Okay, Bismillah ar-Rahman ar-Rahim, wassalatu wassalamu ala nabiyyina Muhammad wa ala alihi wa sahbihi ajma'in. Thank you for inviting me to the KAUST Research Conference on Robotics and Autonomy. I am glad and delighted to provide a talk today about leveraging AI for unmanned aerial systems deployment strategies. I'm going just to take you through the journey I have been working on maybe since a couple of years ago when I have started to do robotics and unmanned aerial systems. And my objective as a computer scientist basically is to integrate mobile robots and drones into Internet of Things architecture and cloud as well. Let me start by providing the outline. I'm going to provide an overview about on our work on the Internet of Unmanned Systems. I will also talk about cloud versus edge AI inference for UAVs, and I will show some of the AI applications that I have been working on. So I am Professor Anis Koubaa, full professor in computer science in Prince Sultan University. I am also the director of the Research and Initiative Center and the director of the Robotics and Internet of Things Lab at the same university. I work on several research areas, and mainly I try to integrate different smart systems together, like IoT, Internet of Things, unmanned aerial systems, mobile robots, artificial intelligence. Okay, let me also give you a brief overview about my research lab, the Robotic and Internet of Things Research Lab. It's the first established research lab in Prince Sultan University, and currently we have 13 research labs at the university. I have around 12 full-time researchers from different categories like senior members, PhD students. We have also co-op students, research assistants, research engineers. We also have a program for inviting visiting PhD students from all around the world to come to the lab. It will be sponsored by the university, and for an internship period that may span from 1 month to a couple of months, up to 6 months or even more. And so the lab has interdisciplinary. We have different type of experts on software development, mobile development, AI integration engineers, UAV experts, mobile robot experts. So we have different types of researchers and skills in the lab, and this allows us actually to work on different types of projects. Okay, let me start by a motivating scenario, something that we have recently done in February 2021. Just I think now drones are a very hot topic, and the drone delivery is one of the hottest applications that we always hear about, but still we didn't see like real world solutions deployed. There are many challenges. Actually, we went through the process of building a delivery drone in the campus of Prince Sultan University, and this is one of the successful demos that we have done. Okay, this is just POC level, but we are working to make this a complete solution. And just developing this kind of application, you will feel that there is pretty much a big gap between what we think it could be done in theory and when and also in when you want to do the things in reality. Things relate to like communication challenges, security, and different types of issues that come with the deployment. But we were successful actually to deploy this application, and our interest here is not only to have the delivery application, but also some additional AI integrated application into the drone. Like for example, we can use the drone for surveillance for surveillance applications, and this will require to inject AI application with drone. And this actually represents very major challenge that can be solved in different ways, as I'm going to discuss in this lecture today. Also, how to communicate with the drone. That's one of the challenges that we have been addressing, because basically I don't believe that drones should be used like point-to-point communication. This is rather restricted to use just telemetry, but we need to integrate the drone into a more holistic ecosystem, considering cloud, 5G, 4G connections, and taking benefits from what the cloud services can provide for the drone, although as a standalone drone system or as a fleet management system. Okay, so my research started a couple of years ago, and I've been working on a project that is called Drone Map. And the objective was actually to power robots and drones with the cloud and IoT. My objective was to integrate the robots and drones. I considered like mobile robots and drones as just mobile sensors, and how we can manage these mobile sensors through the cloud and Internet of Things architectures. So initially, you know, around maybe 2013, 2014, I have started to work on a very simple project. The project was just to develop a robot for office applications. So the objective was to develop a service robot that we can actually send requests or orders through a mobile phone, and the robot will make the delivery between two offices, or maybe it can bring you a cup of coffee from the cafe in the corner. And the demo was successful, but at that time, I have been working with Rust. Of course, Rust is now the de facto standard for developing robotic applications. But there was a big limitation, is that when you want to deploy the robot, and because Rust uses the Rust core, which is like a Rust master that we have to connect to in order to be able to interact and send commands. So you will be confined to very large, very small communication range, which is just the range of a Wi-Fi network. You can use some kind of Wi-Fi extender. Maybe there are some techniques to use Wi-Fi extender, but still you will run into a limited range when you want to communicate everywhere and every time from the robot. Of course, there are some common networking techniques, like for example, using network address translation or kind of proxy. But these kind of things, they will just introduce overhead into the networking setup, which might not be very affordable for all kinds of deployments. So at that time, I started to think that, okay, how we can actually develop a solution that allows us to control and monitor the robot everywhere and at any time. Okay, and so this is, for example, the map that we have built for the College of Computer Science in the building at Sultan University. And now if we want to deploy the robot, for example, just the robot in the whole space, we will find a lot of trouble because of the limited communication range. So this was the trigger point where I have started to work on what is known currently as cloud robotics. So cloud robotics, this is a hot topic that started in 2010, so almost 10 years ago. Okay, so cloud robotics, basically I can categorize it into two main aspects. It's a way to virtualize the access to the robot. Okay, so providing like abstract interfaces, like for example, web services, to access the robot seamlessly anywhere and anytime through software interfaces. And also the second usage of cloud robotics is what we call computational offloading. This means instead of processing the heavy computation, for example, you want to perform deep learning application or extensive computer vision application, instead of doing that inside the robot, you can offload this into more powerful resources infrastructure like cloud systems. Okay, and this will allow actually to reduce the burden of computation on the robot or on the drone or low-cost devices, and put them into the cloud. This is like a very interesting trend since a couple of years ago, not only in the context of robotics, but also in the context of wireless sensor networks, Internet of Things, mobile computing. So the idea is to push the computation from the edge devices to the cloud devices. But of course, there are several trade-offs to be taken into consideration, like, for example, the communication overhead, the computation overhead, the energy consumption for communication, the energy consumption for execution. And these are the things that we have been investigating recently, okay, whether for a particular application, whether it is better to use computation offloading or just process at the edge, because we don't forget now that the edge technology has evolved pretty much very well, and we have a lot of acceleration platforms that both reduces the energy consumption and also accelerate the execution, which can also be embedded into drones and robots. So historically, like there are many pioneer works for cloud robotics, and they consider RoboEarth, which was from 2011, and also Rustling Bridge as the two main leading works around the area. So RoboEarth basically is a platform that allows multiple robots to share knowledge, okay, into common database, and there are some engine that will process this knowledge and will help the robot to take collaborative decision. Okay, so this is basically toward the computation offloading perspective of cloud robotics. Another pioneer work was the Rustling Bridge. And the Rustling Bridge, it actually made an interface for robot operating system that allows web browsers to interact with robots. So they have developed like JavaScript library that will allow web developers to easily interact with robots through web browsers. But the downside of the Rustling Bridge is that it relies on a server that is located inside the robot. So what does this mean? It means when you want to interact with the robot, you must know the public IP of or the IP address of the robot. So if you are in a local network, that's pretty much fine. If you are, for example, if you want to connect to the robot and the robot is not in your local area network, so in this case, you need to do some more workaround to be able to access the IP address of the robot. So this technique is based on WebSockets. So WebSocket server installed in the robot. So I was inspired by this technique, but I didn't like the fact that the server was located into the robot itself. So I was saying, why not to have the server just located into a public cloud? And then we can put together the end user and the robot through the public cloud. Okay, now the typical UAV system is based on point-to-point telemetry. And for example, if you consider PX4 system or Arduino pilot system, they use, for example, the Mavlink protocol to make the communication over telemetry device. And the telemetry device will give you maybe hundreds of meters or maybe sometimes a few kilometers for communication, but still the range will be limited. And of course, with point-to-point communication, we cannot have a scalable system with multiple drones that interact with fleet management system. So the idea was actually, instead of relying on point-to-point telemetry system, is to rely on cloud-based UAV system or robot system in general. And this is like the high-level architecture. So we can have a robot or drone with 3G and 4G connection. So any kind of internet connection. Okay, and of course it can, here we consider the case of ROS-enabled robots, and we will have the end user at the other side, and then through a public cloud, okay, with a non-public IP address and sufficient resources, we will establish the communication between the drone and the end users. And we can take benefit from the cloud, not only to ensure like to be used as a proxy between the robot and the end users, but also it will allow to perform computation offloading. So this kind of architecture, it will address the two perspectives of cloud robotics. First, the virtualization. It means we can develop abstract software resources that will allow the seamless interaction between drones, robots, and the end users. This on the one hand. On the other hand, we can use the cloud to offload computation from the drone or from the robot back to the cloud to be processed, or also can be to the fog systems. So in 2017, I've designed the Rustling protocol. And the Rustling protocol was kind of inspired of the Mavlink protocol, but it was applied to the robot operating system. And the idea here is if you have any robot or any drone with ROS, of course, ROS is the meta operating system that will interact with all the drivers and all the hardwares. So we develop here what we call the Rustling Bridge. And the Rustling Bridge will interact with the ROS ecosystem to take any information that it needs. For example, it will take the information about the robot position, the map, okay, if the robot is navigating in an environment, or for example, the drone velocity, the drone location, GPS location, any kind of information that we can get from the robot. So ROS Bridge will interact through ROS to take any of this information, and then we'll submit it through the internet or through communication networking channels to the cloud server. And the cloud server has another block that is called the Rustling proxy. And here the objective of the ROS proxy is to link the robots and drones to the end users. And the end user will also have what we call the Rustling client on the user side, so that it receives all the information from the robot and the drone to the Rustling client. And of course, the Rustling client, when it receives this information, it will control and monitor everything it needs from the robot. For example, it can send commands for making the robot move, okay, or for example, sending missions to the robot, making the robot stop, or getting any information about the robot. So this was like the high-level architecture of the Rustling protocol. It integrates with any ROS-enabled robot. So we can convert any ROS-enabled robot to an internet-based robot or drone very easily by just adding the Rustling protocol. And the Rustling was developed as a ROS package, so it can be easily downloaded and integrated with any ROS-enabled robot. Okay, so this how it looks like. So for example, in this case, if you have multiple robots, everyone will have its own ROS master. Okay, so in this case, for every robot, we will have a Rustling bridge that will communicate with the cloud through JSON messages, which we call the Rustling messages. So we have a predefined message structure that defines the Rustling protocol. And this will allow to communicate with any user. So I have the first version of Rustling open source, so anyone can download and can use it. It can be easily extended for any type of information with ROS. You can add your own custom messages if you want. Just by reading this paper here, you can understand the overall spirit of Rustling. We have some other versions, but still we are developing it and we didn't put open source. But I have one open source version that is available on my GitHub repository. After all this work, I have been able to make the first successful takeoff and landing in September 2016, after almost maybe around 2 or 3 years of working and development. So this is actually a web-based interface that we developed at that time, and it uses the Mavlink protocol. This one didn't use the Rustling protocol, but just used the Mavlink protocol to communicate with the drone remotely through a cloud server. So this was like the first successful takeoff and landing I've done here in the small area of my house. And later on, we were able to deploy this with the autonomous mission, with the complete autonomous mission. Still here using the Mavlink protocol with this interface. Okay, so you can have in real time all the information from the drone. As you can see, you can define a mission very easily. Okay, so as you can observe, you can define on Google Map a mission and then upload the mission through the cloud server to the drone, and the drone is going to execute the mission, and you can monitor the drone from your web interface. And it was successful. Actually, we tried one time from Saudi Arabia. I tried to fly a drone in China. I had a collaboration with a tech company at that time, and we plugged drone in China. I was able to take it off from my office in Saudi Arabia and just watching how it moves around through the Google Map interface. Okay, so you can find more details about this work in this paper that was published in Ad Hoc Network last 2 years ago, Drone Map Planner, Service-Oriented Cloud-Based Management System for the Internet of Drones. Okay, and actually the system can do much more than this. So here, for example, I have used the simulated drones, and there is no difference of using simulated drones or real drones because all of them we communicate through the Mavlink protocol. So you can see here, we have developed a fleet management system, and this will allow you to automatically detect any drones that is connected to the system. And then you can define missions, okay, for multiple drones. So 1 year later, we've developed a more advanced application that is the UAV follower application. And this application, basically, it uses the same drone map cloud systems that you have developed. And this is the idea of this application. So through a mobile, so here it allows a drone to track and monitor a person using a mobile device. So you have a mobile device, you can request a drone to make a follow mission. And in this case, the mobile device is going to publish and advertise the GPS locations to the cloud, and the cloud will send the GPS location to the drone, and the drone will be following the person. Okay, so this is an example that we have developed in the football field of Prince Sultan University. So through the mobile interface, we can request the drone to make a follow mission. Okay, and now this is the drone starting the follow mission here. Okay, so as the person moves with the mobile phone, the drone is able to follow the person. And of course, here we have, this is just a demonstration, but in the paper, we have analyzed many properties of this kind of systems, like for example, in terms of real time, in terms of impact of communication, what is the delay, the jitter. We have made a thorough analysis of this application. So last year, just before the pandemic, we have also had a successful deployment of a mobile robot through the 5G network. This was in the inauguration of the 5G lab of STC. It's the telecommunication company in Saudi Arabia. And the demo was actually triggered by Huawei company for the inauguration of the 5G lab. And here we can see that we have very smooth performance. So we were able actually to have a real-time stream, as you can see, up to 20 frames per second in high resolution. Okay, so we were able to teleoperate smoothly the robot through the 5G network and also get a real-time stream of the video from the robot. Because in this version, we have also added like a video stream serialization to be able to stream video frames from the robot to the mobile application. And of course, the performance substantially depends on the available bandwidth and the type of network. But of course, with the 5G network, the performance is very smooth. And this is what we wanted to demonstrate at that time. This is an example of another deployment where this is our first trial to make cloud-based deep learning inference using video stream from a UAV. Okay, the quality is not excellent, but just to demonstrate the concept, because here we're using a Raspberry Pi with the Wi-Fi dongle, but usually the communication quality is very low. Although we have operated into 5G network, but the Wi-Fi dongle doesn't give like sufficient bandwidth in order to have high stream performance. But still, we were able to stream. So what you can see here in the back images, it's the images that are received by the cloud and then processed by a deep neural network. I think it's a YOLO detector that is pre-trained on the COCO data set here. So it can automatically detect a person. It can detect different type of objects. This application, basically, when we deployed the video stream on the cloud, now we started to think, is this the best way? For example, if you want to make surveillance application using drones, is this the best way to proceed? Should we actually make live streaming to the cloud and then take benefit from the cloud resources, or it's better to make the processing on board in the drone itself? So we have, to address this question, we conducted a more elaborated study on this topic. So this is the drone that we're using for deep learning inference and also for communication with the internet. So as already mentioned, we start to think what is the best strategy if we want to make AI inference. Should the inference be done in the cloud, or should the inference be on the edge devices? So we've done two types of study, of course, and here we are dealing with deep neural networks. And just an overview that neural network is actually a sub area of machine learning. And we can summarize the difference in that machine learning. It uses manual type of feature extraction. So basically, if we start from an image contains a lot of information, and not all this information is relevant for the classification, for example, or for object detection. So what we do, we first try to extract the most important features, like, for example, vertical edges, horizontal edges, or different type of features or textures. So in the early days of machine learning, this feature extraction was done manually. And then we use different type of classifier, like we use neural network, or we use support vector machine, or nearest neighbors, KNN classifiers, in order to distinguish between these features. But with the revolution of deep neural network starting from 2012, both feature extraction and classification are performed into neural network. And this is possible because we have more powerful devices. The GPUs now, the GPU devices allows to process huge amount of data and allows to perform both feature extraction and classification at the same time. Deep learning now is maybe one of the hottest, if not the hottest area in information and communication technology. We proposed the deep learning, the deep brain architecture, which is an architecture for the inference, or for, let's say, for inference from UAV devices, from UAV platforms. So here you have a UAV. Basically, UAV will just take pictures. We'll collect pictures from a certain environment. And then these pictures will be transferred to the cloud. It can be processed locally, okay, because we have some kind of edge devices that can be embedded into the drone. And we can have also another level of edge computing, which are more powerful servers that are in the proximity of the drones. And this will allow fast processing of the information. And also we can relay these images, or for example, for more heavier type of computation into more sophisticated clouds. And on the other side, we have like the users using some kind of dashboards and control stations in order to interact with the whole system. So this is basically the architecture. And of course here, when we deploy the architecture, real time is very important because, for example, when you have surveillance applications, you don't want to spend a lot of time to detect any event collected by the drone. So basically, you need to have a delay less than 1 second or 500 milliseconds, depending on how critical the information is. We want also to develop scalable scalable architecture that allows to have hundreds of drones or probably thousands of drones all managed through the same fleet management system. The system should also care about energy efficiency to extend the lifetime of the drones, because we don't forget that the drones are battery powered, and battery is actually the biggest issues now in the drone technology, because using battery resources or for energy, it doesn't allow very extended lifetime for the drones. I think now current commercial platforms, they span from 30 minutes to 1 hour, maybe in some cases 1.5 hours, but not more. And this also heavily depends on the type of payload on the drone. Security, safety, and reliability are also very important topics. So this is the deep brain system component. It was like an extension of the drone map architecture. We still use the Rustling Bridge protocol with some extended features. We use WebSocket UDP for communication. And here in the back end, we have deep learning module for receiving the images from the drone, process them, and send the result to the end user. For computational approaches, there are two types that we would like to investigate. So if we do the processing on board, on the drone itself, so in this case, we will have large processing delay and low communication delay. Why we will have this one? Because we will not transmit the images. We will not transmit the images to the cloud, but we will process the images in the drone or in the embedded device, and then we'll just forward or transmit the result only, which is just some textual information. Okay. However, if we perform computational offloading, in this case, the communication delay will be larger than the processing delay, because we will need like sufficient bandwidth to transfer images from the drone to the cloud. So there is a trade-off to do, okay, between communication delay and processing delay. And this is what we try to investigate into this paper that is about deep brain. Some other application like face recognition, here we have only two possible approaches, for example, for traditional object detection or classification. But for our face detection, for example, or face recognition, we can have three types of deployment strategies. So face recognition, just to summarize, we can start by an image, and the first step is to extract the face, okay, using some face detection algorithms. So we'll have here a bounding box, and then the extracted face will go through a convolutional neural network, for example, like FaceNet, and then it will generate a one-dimensional vector, which we call the face embedding. It's kind of a footprint of the face. And this footprint will be compared with other footprints that are stored in the database, other face embeddings for existing users, to finally recognize and identify the person. So this is actually the whole loop. So here we have two bottlenecks in terms of processing. The first bottleneck here is the face detection, which also can use neural network. And the second bottleneck is the face recognition. And this is why now, when we want to deploy this, okay, we can deploy it on a drone or any kind of camera. There are three types of strategies for the deployment. The first type is to make the face recognition completely on the cloud. So what does this mean? It means that the camera or the drone will be just a sensor that captures the image. It will not do any processing. It will capture and then stream. Then it will send the image, for example, in base64 format. And then inside the cloud, you will perform both face detection and then face recognition. And finally, we'll get the result to the end user. The second extreme case is to do the face recognition on the edge. So in this case, the drone or the camera will be attached to an edge computing device with a GPU, like for example, Jetson Nano or Jetson NX. And this will allow actually to make local processing of the face detection and recognition. And finally, we can send the whole result. So only we can send the identity. We can also send the image itself if we want, and then put everything here in storage. So the cloud here will not do any processing, will just be like a place where to store the detected events or the detected faces. And the third type of deployment is the hybrid deployment. And here, so we will do the face detection with tracking on the edge device, and then we will perform the face recognition on the cloud device. So we have made a holistic, like comprehensive study about what is the performance of these different type of deployments, which I'm going to present in a moment. So the first work, coming back to object detection, and this work was published in MDPI sensors. So we consider 3 scenarios. First, we have evaluated the energy consumption, the cloud server utilization, and real-time guarantees. So for energy consumption, we have observed that when we perform the processing on board, okay, so this will increase the power consumption by a factor of 2. Okay, so here just without computational flooding, we have 3.2 watt instant power consumption on a Raspberry Pi, and on local processing, we have 6 watts. Of course, if we use some other types of embedded devices like Jetson NX or Jetson AGX, we can have even higher power consumption because depends on the maximum power allowed by the edge device. So basically, it's can go to 10 watt or 20 watts, can go even to 30 watts. We have also investigated the impact of the bandwidth. So as you can see here, in the plot here on the top, we use computation offloading. Okay, and we have started 5 drones streaming videos over the cloud. And you can see here the shape of the bandwidth over time. And just here below, same thing, but without computation offloading. And you can see big difference in terms of bandwidth consumption. Just for 5 drones here, we consume 3 MB. Okay, so now we can imagine if we go much higher in bandwidth. Of course, this depends on the frame per second, the frame rate, and the image resolution that is used. But of course, there is a big difference, as you can see here, even in the statistical plots. There is a huge difference in terms of bandwidth when we use computation offloading and no computation offloading. And this is something that has to be considered and be taken into account when deploying the inference on the cloud. Also, we can use compression in order to reduce a little bit the bandwidth consumption. For the cloud execution times, so we have also measured the average execution times using computation offloading. The average cloud execution time is at the order 7.25 milliseconds. So here it means the deep learning neural network is executed on the cloud. And this is why we have 3 times higher execution times as compared to no offloading. So if we don't use computation offloading, it's only 2.25 milliseconds. The end-to-end delays, we have considered a bandwidth of 50 megabit per second over a 4G network, and we considered image size of 824 kilobit for non-compressed image and 350 kilobit for a compressed image. And you can see here that the end-to-end delay, if you use just the raw image, it can go up to 3.2 seconds in average. But the maximum delay here, you can see it can reach up to 5 seconds in average, maximum of 5 seconds, which is pretty much high. And using compression, this allows actually to reduce the end-to-end delay to 1.7 in average and 2.5 maximum delay over here. And you can see without just streaming images, it's the end-to-end delay of communication is pretty much negligible. It's only 500 milliseconds. So streaming over the cloud also has an impact not only on the delay, but also on the jitter. We can have a jitter as high as 2.4 seconds in average for raw images and 1.2 seconds if we use compressed images. And this is also for the frame rate. the frame rate may increase to 4 frames per second, from 1 frame per second to 4 frames per second if we use image compression. And then later on, we have also considered, okay, what if execute the deep learning algorithm on different type of devices? So we wanted to compare the impact of the GPU type on the inference speed. And for this, we have considered some cloud-based devices. So RTX 2080 Ti with 11 GB and GTX 2080 for cloud-based devices. And we've considered the Jetson Nano with 128 core Maxwell GPU and the Raspberry Pi 4 for Broadcom. So these type of devices, they are typical devices for edge, and these type of GPUs are typical for cloud. And here we can see that we have a big difference in terms of the execution time. So it's much faster, so we can reach 14, 12 frames per second on cloud-based servers and just 1 frame per second if we run on edge devices. So there is a big trade-off to do between cloud execution time, communication delays, jitter, so many combinations of factors that have to be investigated when you want to deploy UAV application over the cloud. I have some more slides about inference. And so this is just an application that we did for real-time inference on face. And I want to talk a little bit about different types of optimizations and acceleration frameworks like TensorRT and TensorFlow Lite. Finally, we've also done some traffic analysis from UAV. We have a solution that allows to extract different traffic information from a UAV, like for example, the speed, number of vehicle crossing the intersection, and we can extract different types of information, like for example, the velocities of the vehicles, and also the congestion map. So for example, you can extract what are the areas that are more consistent than the others from the analysis of aerial images using deep learning. Okay, thanks for watching.
But thank you very much for your presentation.